Welcome everybody to another session from Narrow Research. I'm Srijit here, and in this session, I'm going to brief about TD-CDFT for 2D periodic systems. So for periodic systems, especially two-dimensional, like monolayer materials, calculating the response properties using time-dependent CDFT with a new response method with AMS band is a powerful approach. So as an introduction, I would like to brief what is actually TD-CDFT. So 2D materials and their unique optical properties includes, or which are characterized by their atomic scale thickness, leading to strong quantum confinement effects. This dimensionality reduction significantly alters their electronic and optical properties compared to their bulk counterparts. For example, many 2D semiconductors exhibit direct band gaps and strong excitonic effects, leading to unique optical absorption and photoluminescence. Accurately modeling these properties, which requires methods capable of handling periodicity by accounting for reduced dimensionalities. And speaking about time-dependent constraint density functional theory, or TD-CDFT, for optical response, is an extension of a DFT which allows the calculation of frequency-dependent response properties. In the calculation for optical properties, the primary output is typically a frequency-dependent dielectric function. From this, other optical quantities like absorption spectra, refractive index, and reflectivity can be derived. So TD-CDFT in band is based on time-dependent current density, which is particularly robust for periodic systems. And speaking this method in AMS band, speaking about AMS band, it's a module in Amsterdam Modelling Suite dedicated for TFT calculations of periodic systems. We have recorded multiple videos on that earlier, and it's well suited for crystalline materials, including 2D systems, 1D systems like nanotubes, and 3D bulk solids. For more reference, you can visit our YouTube channel for more information about those basic videos. So the new response method. So in AMS band, the TD-CDFT calculations for response properties have two main implementations: old response and new response. The new response method is the more modern and generally preferred approach, especially for 2D systems, due to several advantages. And support for two-dimensional systems, the new response method is explicitly designed and optimized for 2D systems, while old response has limitations for these. So this is a crucial distinction when working with monolayers. And about the algorithm, it relies on more reasoned and efficient within the band core, leading to improved performances and numerical stability. And improved handling of k-space. So calculating the response properties in periodic systems requires accurate sampling of the reciprocal space, which is known as k-space. So the new response offers enhanced capabilities for k-space integration, which is critical for converging the dielectric functions. So which will be typically in systems with sharp features in the electronic structure. And new response introduces specific input key blocks like new response, SCF, new response k-space that provide fine-grained control over calculation parameters, and which allows more tailored and accurate simulations, which includes frequency range that defines the starting and ending frequencies and the number of points to sample, and then the energy shift. This parameter can be used to manually adjust the band gap to the correct DFT underestimation of the band gap in semiconductors or insulators, and then the volume cutoff or density cutoff. For one-dimensional and two-dimensional systems, the unit cell volume in the non-periodic direction is undefined. So band can address this by allowing the user to define an effective volume-based density isosurface, and then active energy space, which modifies the energy threshold for including single orbital transitions. So these are actually the properties which we can, or the options which we can include in new response calculations. And then speaking about the workflow, as I said earlier, we have already generated this system and the band gap calculations in our previous videos. So I'm not going into depth at how we can set up the calculations. I'm just showing you that what are the methodologies which can be offered or be included to cover up this new response method. So in the initial geometry setup, we have to create a two-dimensional periodic system. I have already created a mono layer, molybdenum disulfide, and it ensures proper vacuum layers in the non-periodic direction. And the ground state calculations, to perform a ground state DFT calculation using band, it's crucial to use the same basis set, numerical quality and case-based sampling for the step as we intended in the previous band structure calculation. So I have maintained all the same methodologies, and for covering up TD-CDFT calculations, we have to navigate to the properties. I'm just showing you the properties. So this is actually this band structure which I have already calculated, and now I will show you that what is actually this calculation which I have set up for TD-CDFT. So under properties, I have selected this new response method. So we have to define the frequency range, the number of frequencies, and any necessary energy shift. So the frequency range has been selected here from initial, final, and the number of steps, the criterion. So after defining the frequency range, we have to uncheck this set box for components for our 2D materials which lies in XY plane. So I have unchecked this component, Z component, which is very necessary for the optical response in primarily in the plane. And then I have adjusted the volume cutoff based on the density of 2D materials to define the effective 2D volume of the calculations. So this is actually the method, and then after executing the calculation, which I have already done, so which will take some time. So I am just going to this spectra. So the spectra will brief you that what are the things to be covered as a part of analysis. So after the calculation, we use this AMS spectra to visualize the real and imaginary parts of the dielectric functions and derive the absorption spectra. So this is actually the absorption spectra and the dielectric function along XX. And to summarize, the new response method in AMS band is the state-of-art approach within the AMS suite for calculating accurate frequency-dependent optical response properties of two-dimensional periodic materials using time-dependent CDFT, which offers improved specific functionalities for the unique characteristics of low-dimensional systems. So this is actually the overview about how we can perform a new response method within AMS band. And for more information, I request you to kindly subscribe our YouTube channel. As I said earlier, we have launched multiple videos covering the properties of periodic systems, and I request you to follow our LinkedIn page. Thank you.